everyone. Welcome to this month's Astronomy on Tap. Thanks for being with us. I am your host, Courtney, and we're coming to you live today from Baton Rouge. This month, we have two actual local speakers for you guys, a rarity in this virtual era of AOT, and both of them are professors from LSU. Before we get started, we have the usual ground rules. Number one, be considerate in the chat. We've never had an issue, but it's worth saying. Number two, feel free to drop any questions that you have for the speaker at any point during the talk. And at the end of the talk, I will field them to the speaker for you. Number three, please consider donating to our Venmo or our PayPal. And as per usual, we like to add some competition. So this month, we want to know if you prefer lunar or solar eclipses. This past month, we've actually had both types. There was a total lunar eclipse on May 26th and an annual or solar eclipse on June 10th. And there are a whole bunch of good photos online if you want to see some better photos of them and see all of their brilliant glory. So if you do make a donation to us, make sure in the memo section you write down if you prefer a lunar or a solar eclipse. And number four, the last one, please like this video if you're watching and subscribe to our YouTube channel because it does help us out so much, gives us a lot more visibility within the YouTube algorithm. So without further ado, I'll move right on to today's talks. So first up, we have an LSU professor with some interesting animals, most notably his array of chickens and his very large cat who eats 5 meals a day. And he's here today to tell us about graphene usage in technology. Please join me and welcome Dr. Dan Sheehy.
Hey everyone. Now I just got to share my screen. Let's see. Gotta get this thing going. And cool. So cool. I'm excited to be here. Thanks for joining my talk. I'm going to tell you about graphene. And so the title of my talk is Space Age Material for Future Technology. And I guess with that title, I'm just trying to get you excited about the possibilities of this new material that was only discovered just a handful of years ago. So I'm a professor at LSU, and you can send me an email if you have any questions or if you want further discussion. So here's an outline of my talk. So what I want to get across today is that future devices and technology are going to rely on building materials atom by atom. So you know that nowadays technology is exploding, our phones are getting faster and faster, but we're not quite at the atomic scale. We're almost there. And one material that's sort of leading the way is graphene. So graphene was discovered in 2004. It's the first known two-dimensional material. I'll tell you about it in detail, and I'll try to tell you some cool applications for it. So you should think of this new material as a totally new building block for future devices. So on the right, I have something called the space elevator. I'll tell you what all these things are. So this is something called the space elevator that might be possible with graphene. And I'll also tell you about some sort of superstructures that people are proposing to make with graphene. So I realize this is an astronomy seminar series, and I'm a little bit nervous because I'm not an astronomer, so I have to get that out of the way first. I'm actually a physicist, so I'm a condensed matter physicist, and what I'm going to tell you about comes from my expertise in this area. So I have to start by telling you about condensed matter physics. So what is condensed matter physics? So essentially, condensed matter physics is the study of materials. So here you have a material you've probably recognized, that's gold. So gold has certain properties that we all know about. It's malleable, it's ductile, it has a certain color that everyone loves, but it's also a type of atom. So gold is an element. It has a certain number of protons, neutrons, and electrons. And so you might say, well, gee, if I take these gold atoms and I stack them, right? That's what nature does. Nature stacks these atoms for us. How does gold, the material, emerge from this stacking of these atoms? That's what condensed matter physics is about, right? So the question is that, how many gold atoms do you need to make the material that we know and love? So the question is, it's actually very hard to answer that question. But what I'm going to tell you about now is essentially how there's really a lot of gold atoms in any piece of gold. So I want to get across how small atoms are. And so any piece of material just has a ton of atoms in them. So let's try to estimate how many atoms there are. So atoms are very small. So you probably knew that. Atoms are the building block of all materials. And one way to measure that is to sort of ask how many atoms are there in a certain piece of material. So one way to measure that is through something called a mole. I don't know if you've ever heard of something called a mole. You might have learned about it in chemistry class. So it's not this kind of mole. It's a different thing. It's a mathematical symbol, and what it essentially means is that you know that a dozen means 12. So that means that somebody decided that the best way to measure eggs is using a dozen eggs. A mole is this many. So this many atoms. So the reason they came up with this number is essentially because in order to describe materials, there's so many atoms in any piece of material that you've got to measure them in terms of these units, right? So for example, an 8-ounce glass of water has 12 moles of water molecules. It's such a huge number, it's hard to imagine the implications of so many objects in this glass of water. So I have a thought experiment I like to I give. So usually, I don't think we can do this on the YouTube, have an actual quiz, but usually I give it as a quiz. So here's a thought experiment for you to think about. So imagine if you had 1 mole of marshmallows, right? So this many, 6 with all those zeros. If you had that many marshmallows, how much volume would that occupy? A, would fill the room that you're in, would fill Tiger Stadium. So this, I'm assuming people know about LSU stuff, even though this is a worldwide YouTube video, would fill the Superdome, another Louisiana reference, or would cover the Earth 12 miles deep. I'll assume everyone's thinking about which that is. The answer is D. So don't worry, we're not going to do this experiment. This is just a thought experiment to imagine, just the sheer largeness of this number representing the size of an atom. Okay, so representing how small atoms are, right? So now that I've sort of gotten across how small, or rather how many atoms there are in any piece of material, we can ask, how small are they really? Like, how small is an atom? How do we think about that? Well, they're very small. So here's my cartoon picture of an atom. This is sort of a cartoon. It's approximate what you're supposed to, you've probably seen images like this before, like in cartoons or in textbooks, if you like to read textbooks. So it has a central nucleus. A nucleus is only 1/10,000th of the volume. Most of the volume is just electrons buzzing around. So these little orbits are representing electrons buzzing around on this atom. And so what that means is that most of the volume of matter is empty. It's just filled up by these electrons buzzing around. Okay, so here I have sort of listed the size of an atom. And so that means that it's about 1/1,000,000th of the size of a human hair is one way to think about how big an atom is. Very small. Human hair is really small, and this is much, much smaller than that. So if you have a material, so any material like a piece of metal or something like that, essentially what happens is that the atoms form like an array, right? So they're stacked just how you would stack oranges in your kitchen or at the grocery store. And what happens then is that the electrons in this material, they detach and they roam around. And so if you have a piece of metal, metals are shiny. All of that is determined by the electrons in these materials. They control all the electrical properties. So whenever you have a piece of wire that's controlled, the properties of that wire are controlled by are determined by the electrons in that wire. So here's another thought experiment. Does anyone know, and I know you can't answer, but you should still think, as a fun thought, how big is an electron? So an electron, that's these buzzing things around this atom. Electrons, this electrons, when electricity flows through a wire, it's just, think of that as like a river of electrons flowing. How big is an electron? The answer is no one knows. It's actually an unsolved problem in physics. No one knows. It could be, no one knows. I'll leave it at that. We know that it's smaller than 1/1000,000th of a meter, though. And actually, we know that it's smaller than 1/1000,000th of a billionth of a meter. So we know it's very, very small. So, what I want to tell you about next is the implications of the smallness of atoms. Just to think about, what does it mean that everything that we're made out of, everything is made out of these tiny little building blocks. So think of those building blocks as being tiny little Legos. They make up all of matter. And there's a great quote from the famous physicist Richard Feynman, where he pointed out in 1959 that there's plenty of room at the bottom. And it's kind of a funny phrase, and I think it's really interesting to think about what he meant. So before I get to that, I want to mention that Feynman won the Nobel Prize in 1965 for a theory of physics, and he also was instrumental in figuring out the cause of the Challenger space shuttle disaster. So he was one of the leaders of the team that investigated that. So these are some of his major achievements in science. And so what he meant by that there's plenty of room at the bottom, what he meant is that the room is the room to shrink devices, right? So he knew way back in 1959 that the future meant that there's going to be smaller and smaller devices, right? And we, of course, we all know about this, but he had an interesting quote. At the time, he said, the information in all the books in the world, 24 million or so, that was back in 1959, can be fit on a tiny piece of dust, 1/200th of an inch on one side, right? So that's kind of a funny thing to think about, actually writing with atoms. And if you could write with atoms, all the information in all the books in the world could be fit on a tiny piece of dust. So that's how he thought about the fact that there's plenty of room to make devices smaller and smaller. Of course, you know about this. He was totally right. So you know that this idea of there being plenty of room at the bottom has led to the computer revolution, right? So here's a picture of, and I know everyone on this call knows about this important aspect of all of our lives, that computers used to be room size. So here's a state-of-the-art computer from 1964, and now, of course, as you all know, your smartphone is much, much more powerful than that old IBM. Sorry, my Alexa just turned on. Alexa, computer off. Computer off. Sorry, my Alexa just turned on during the call, so that was funny. But to get back to the lecture, this is a stated, so as you all know, this room to shrink devices has led to the computer revolution. So we know about smartphones. We all know about this, but what you might not know is that we're not done. We're not done making smaller and smaller devices. Current technology is still really big compared to the size of an atom. So even though we have these incredibly smart computers and smartphones, the current technology is still really crude when it comes to the scale of an atom, right? So the smallest, even though there's all these millions of transistors, the smallest features in these are thousands of atoms across. So that means there's even more room. There's additional room left to shrink devices smaller and smaller, and that's where the future is going. But the question is, how do you make a material? How do you really start to arrange atoms one by one to really make the smallest possible and therefore most powerful devices? And one answer to that is a material called graphene, which it was discovered in 2004. So now I'm going to tell you about graphene. So let's get into it. So it's actually really simple. So you've probably heard of graphite. Graphite is a crystal of carbon. So it is pencil lead. So if you write with a pencil, you write with something called graphite. So what is graphite? Graphite is a crystal of carbon. It's different from a different carbon crystal. So here's diamond. You know about that one. So we're not talking about diamond, but I just had to show it because we're mentioning carbon. It's a crystal of carbon. So if you were to zoom in on graphite, you would see it is composed of these thin layers, okay? And so that's why a pencil works. So when you write with a pencil, these thin layers come off, and that's what you see when you write on a page, okay? So it's these thin, weakly coupled layers, and these layers are all made out of carbon atoms. So these little dots are meant to be carbon atoms, and they're linked by bonds. The carbon-carbon bond is the strongest bond in nature, so it's a very strong material. But it's weakly coupled in the layers. So, so what's graphene? Well, it's just one of these layers. So literally, the subject of this talk is literally a thin sheet of graphite that they were able to isolate. So it was first proposed back in 1947, but no one made it. No one knew how to make it. And really, what the problem was is that people sort of thought that it probably wasn't stable. But of course, somebody eventually did make it, but not until 2004. Okay, so it's very thin. So what that means is that if you were to take a millimeter of graphite, that would be about 1.5 million layers of graphene. So very thin, these very thin layers. And you have to think, how would I isolate one sheet of this graphene? So it was actually first isolated in 2004, which is very recent. It's in terms of scientific development. And I'm going to tell you next about how they did it. So the question that we want to answer next is how to make graphene. So it turns out to be really simple. It's the same way you get cat hair off a white couch. And this is literally what they did in the experiment. This is not a joke. And the cat hair part is a joke. But essentially what they did is they took Scotch tape. So what they did is they took graphite, put Scotch tape on it, ripped off the Scotch tape, and then that left a few graphene layers attached. Then they put it on their substrate so they could do an experiment, and then they removed the tape. Okay, so this is how they made graphene. So this development, the Scotch tape method, and of course the experiments that they did with it, won these authors, Geim and Novoselov, the 2010 Nobel Prize in Physics. So an interesting side note about Andrei Geim, Novoselov was the student, Andrei Geim was the advisor. Professor Geim also won the 2000 Ig Nobel Prize for levitating frogs in magnetic fields. So I won't have time to talk about that, but that's another thing that he's kind of an interesting character. He also did this other work, levitating frogs. He's very prolific, interesting person. So that's another thing that he worked on. So what are the properties of this material, graphene? So literally you should be thinking of this super thin sheet of graphite. So some of the properties of graphene. The atoms in graphene form a honeycomb crystal. We know what that looks like. We know what a honeycomb looks like. So here's so that's obviously a joke image of honeycomb cereal that I used to eat when I was a kid, but here's an electron microscope image, and you can see that these carbon atoms are forming a nice hexagonal array. And that hexagonal array is very strong, and the carbon bonds are very strong. So the carbon-carbon distance is 0.14 nanometer, and I know I'm supposed to keep this non-technical, but just to remind people, 1 nanometer is about a millionth of a millimeter, so it's a very small distance. It's actually a very strong material, and that's because the carbon-carbon bond is so strong. And so what that means is that if you roll up graphene into a tube, and that has been done, it's called a carbon nanotube, it's actually a very strong wire with very high tensile strength. But what's also interesting is that it's light and foldable. Okay, so it's a very floppy material, it's foldable, and people have done experiments where they do what is called graphene kirigami. So I don't know if all of you have heard of kirigami before. You've probably heard of origami, which is folding paper. They've done that with graphene, but kirigami is the art of cutting paper into interesting shapes to have a certain function. And that's been done with by the McEwen group at Cornell, real experiments. So now this picture, of course, here, this is not actual graphene. Here's the real graphene. And it's really hard to see, but this is actual graphene that has been cut in the same pattern as this paper on the left to create a kirigami structure. So, okay, so I have to get into astronomy because this is an Astronomy on Tap talk. Well, there are possible applications of graphene in astronomy. So one application is due to the fact that, as you may know, launching stuff into orbit is very expensive. So why not put a rope into orbit? This is a proposed idea to make it easier to get stuff into orbit. Now, this sounds crazy, but if you could have a rope that was strong enough, it could go into geosynchronous orbit. And essentially, what you would do is you would attach something to the rope, and then it would go up the rope, just like rope class in climbing the rope in gym class. It will take a very long, strong rope. And this is a proposed device. It's very far in the future. It's called a space elevator. No material is strong enough except graphene. So graphene may be possible to make this device. There's obviously, it still sounds kind of crazy, but it may be possible with graphene-based cable, and people are working on this right now. So that's one possible idea, space elevator. Another possible application is due to the fact that rocket fuel is also very expensive. There's an easier way to have a spaceship move in space through what's called a solar cell, where you have a solar sail where a sail essentially captures light from the sun and allows a spacecraft to move without fuel. And this has really been done. So there's a space probe that was launched in 2010, not with graphene, but with a different type of sail. So I kind of like this acronym. It actually, interplanetary kite craft accelerated by radiation of the sun. I think it's cool that it worked in kite because that's what it is. It's sort of a huge kite that was launched into space. And what would be really cool is if they could make this, and people are working on this now, it's the idea of making this, this sail actually using graphene. And then it would potentially lead to a stronger and lighter solar cell. So graphene is also transparent, is something I wanted to tell you about. How would you measure the transparency of graphene? Well, it's very simple. You would just shine a light through graphene, and here's the human eye on the other side. Turns out graphene is almost perfectly transparent. So it's like a very thin sheet of plastic wrap or something like that. So what this means is that it's 97.7% transparent. And so actually this is an image from the experiment where they did this. So this is just an aperture where they covered it with graphene and they just looked through it. Not with a human eye. They actually had a scientific experiment that carefully measured the light, but actually what they found is that, so here's a region of air and here's a region of graphene where you can see that the difference is only 2.3%. So it's very high transparency substance. So this is, it's incredibly thin, strong material. And so this could lead to what's called a graphene solar cell, which might be possible in future technology. So I'm running low on time, actually, I realized. And so, but I wanted to talk about something called a moire pattern. So graphene, a recent development in graphene is to essentially create what's called a moire pattern in graphene. So what's a moire pattern? So moire is a type of French textile which has these beautiful patterns in it. And a moire pattern, more generally, is it's something that is studied in art and in technology and in science, where you have two similar patterns and they can interfere. So for example, here's a moire pattern. So I just have I've superimposed two sets of lines and I've twisted them relative to each other. And you can see that it creates this additional pattern that's an interference between two similar patterns. Here's a picture of fences on a beach. So this is another type of moire pattern. So sometimes you also see moire patterns in like window blinds. So you've certainly seen stuff like this before. But it turns out they did an experiment where they did this with graphene. So they were able to take two sheets of graphene, twist them, and stack them and make a moire pattern. So here are two stacks. This is just a cartoon picture of two stacks of graphene. One is twisted left and one is twisted right. And if we stack them, we make a moire pattern. So they did this experiment. Why is it interesting? Well, it turns out that if you do this to graphene, it becomes a superconductor. So a superconductor this was something that was only observed a few years ago. It was an explosive experiment that people are really excited about. I don't know if you know what a superconductor is, but it's essentially a material that passes electricity perfectly. So I have a slide where I discuss superconductivity, but I'm going to skip over that because I don't want to go over too much. And I want to just get to my final slide where I sort of summarize. So, this is the first two-dimensional material that's ever been discovered. You know that technology is getting faster and faster. Devices are getting smaller and smaller. But if you want to make a really small device, you need a small building block. So if you made a miniature house, you need to have small wood. If you want to make the best, most powerful small devices, you need something like graphene that's intrinsically two-dimensional. So it's like plastic wrap at 50,000 times thinner, and it conducts electricity, and it's super strong. So there's just a ton of possible applications, including a possible graphene solar cell. There's medical applications that I haven't discussed, a graphene light sail I briefly mentioned, graphene space elevator for future technology, and I also mentioned graphene kirigami. And so, so that's all I have to say about graphene. I just want to briefly flash my animals that were mentioned before by Courtney. So here's my chickens, Chloe, Flossie, Colette, Mona, and Lisa. Bernie, my cat, he's ready to go into space. I'm going to discuss that with Dr. Tabby next. And here's our dog, Belle. So thanks, everyone, for listening, and I will stop sharing.
Okay, yeah. awesome talk. I'm very glad that the animals made a cameo. I wasn't expecting that. Okay, so how I normally do this is I start with a few questions about you, because AOT is at its heart about the speakers, and so we want to know you a little bit better. I'm going to start with one that you may not know, but you're definitely one of the most beloved teachers by graduate students at LSU. So I wanted to ask you if you felt like teaching was one of your passions. Is that something that you like try really hard for, or does it just come naturally? Like, what do you think about that?
I think about how to teach a lot, in the sense that I think about physics a lot, and I think I'm good at figuring out the other person's perspective. So I think I'm better like discussing one-on-one. But yeah, I think I work hard at thinking about the best way to explain things. I spend a lot of time thinking what are possible misconceptions, and then I try to circumvent those possible misconceptions. So cool. Next one I have is sort of a generic one, but do you have any hobbies like outside of physics that you want to share? So I have, I play the guitar a little bit. Oh. I like to do crosswords. So I like to do crosswords. I get the paper every week and spend the whole week doing the Sunday New York Times crossword, which is really hard. So I just work on it a little bit. And other hobbies, I like to swim. That's about it. What kind of like music do you play on the guitar? Do you do like acoustic, electric? Acoustic mostly. I used to do electric when I was younger, but now I just do acoustic. I still have the electric guitar and the amp, but I'm not allowed to get it out, I don't think. Yeah. It's really loud. Family. I should get it out. So also, what does a normal day of work look like for you? You work in a lab, right? So are you still working in the lab? I mean, I'm a theoretical physicist. So what I do is develop just physics equations that can describe nature. And so I collaborate with other scientists at LSU around the world to try to understand nature. So yeah. All right. A lot of equations. Totally forgot you were theoretical. Oh, no worries. And then the last question that I have about you personally is a question that we do in honor of Tabby's son, Jude, which is, what is your favorite Pokemon? My favorite Pokemon? Pikachu. Okay, good answer. Yeah. You know why? Because that's the only one I could think of. Yeah. All right. Alrighty. So we can get started with some science questions as well. I wanted to ask you a really basic question, and you might not know the answer, and that's all right. But why do they call it pencil lead when it's actually carbon? Do you know? Oh, I think it used to be actual lead. Did it really? I think so. Okay. Well. And then they changed the graphite, but they still call it lead. I heard that somewhere, but yeah. All righty. I'll Google it. Our first question from our live audience is from Nikki Purifurgun, and they're asking, does graphene occur naturally in space? Like, for example, fullerenes were found in space. It probably does. But I don't know for sure that it's been detected in space like fullerenes have, but it probably does. It's like fullerenes, it occurs in things like soot. So the graphene was around, people just never knew about it. Do you think it would be in something like a dust grain, like there are graphite dust grains? Do you think it would be like that? Yeah, I think that's very possible, yeah. Okay. Our next question is from Rob Parks, a former LSU faculty member. And he asks, how easy is it to manufacture and manipulate graphene? Well, it depends. It's hard to make big sheets of it. That's really difficult. It sort of depends on what quality you're looking for. So meaning there's different qualities of graphene. But if you just want to do experiments and only need a little bit, then people use the Scotch tape method, and it's pretty easy to use. There's more recent developments where they've learned to encapsulate graphene in things like boron nitride, which has a similar crystal structure, and that makes it sort of easier to do experiments with it. So, but it's a huge area of interest to try to figure out how to make it, construct it more easily and make bigger sheets of it.
So with the Scotch tape method, how do you get it off?
I don't fully know. I mean, basically it just comes off, and the hard part is they need to use a microscope to find it. So that's what I didn't mention, is that you imagine these flakes come off, and then you have to get a microscope and find the flakes. And they basically, one of the other things that they did is they had a smart way to find the monolayer flakes by looking at an interference effect. So it sort of made it easier for them to find. Because you might say, how do you know if you have a 2-layer piece of graphene or a 1-layer piece? But they had a clever way to find them. And I can't remember all the details of it, but it was essentially a smart way to isolate, to use sort of an optical image to see where is a single monolayer.
Cool. Brian asks, does graphene exhibit chirality?
Does graphene exhibit chirality? That's a good question. So, that is a good question. So, so certainly if you put it in a magnetic field, it will exhibit chirality. That's a question I could give different levels of answer to. But you mean like optical chirality, or do you mean like electronic chiral edge states?
Well, we'll give him a few seconds to clarify if he wants. Good
question.
A very specific answer or a very general answer. But I will give you a very simple question. If you just graphene is conductive, right? Mm-hmm. It's super conductive almost in those patterns. But if you just take a pencil and you draw a line on a piece of paper, would that conduct electricity in the same way as graphene, or is it a thicker layer?
It would be thicker than graphene, but it would have similar properties. Actually, now I think I know what the question was. The question was asking if it's chiral in the sense of a molecule. In that sense, it's not chiral. Okay. It doesn't have a handedness to it.
Okay. And I have one last question for you, unless someone throws the last one in there. But, you're working with, or you're studying or thinking about heavier molecules than hydrogen, which is, what we're working with in astronomy. And those are formed in supernovae. So are you interested in formation of those molecules or atoms in supernovae and kilonovae? Do you follow that literature at all? Is that something that you ever look into? Or is it just here on Earth, I like it?
Yeah, I think I only follow it in the sense that I go to talks where people talk about where matter comes from in supernovae. And I think it's really exciting. I think there's a lot of mysteries, as I understand, all these different processes that can lead to matter formation, and the rapid and slow processes in synthesis of these types of atoms. So that's definitely not my area of expertise, but I think it's really interesting. So yeah.
Alrighty. Well, if there are more questions, you can jump into the YouTube chat and answer them if you feel so inclined. Mm-hmm. But we are going to break for an intermission. It's only going to be about 5 minutes. So we'll just give all of our viewers about 5 minutes to grab a drink or whatever. And we will be back at 7:40. But in the meantime, I would like to humbly ask you once again to consider donating to our Venmo or PayPal. And if you do, in the comments, let us know if you prefer solar or lunar eclipses. And we will be back at 7:40, so I will see you all then. Welcome back, everyone, to our next half of Astronomy on Tap. I won't bore you with any of our little announcements or anything, so we'll go straight into the second talk. Next up, we have another LSU professor. She's got a bit of a following. She's mostly known for her work on the star that's named after her, Boyajian star. But she's also a great ceramic artist. You should check out her Etsy. It's called Kepler's Kiln. And in addition, she's an avid fan of jam bands, so definitely ask her about that. So today she'll be telling us about cats in space. Please join me in welcoming Dr. Tabby Boyajian.
Thank you, Courtney. How y'all doing? It's good to be here, even though we're not there, but I mean, we're still kind of together, even if it's virtual. All right, so let's get this started. I do have to say that, there is, I am not alone where I am. What did you put on my head? I had so much fun putting this talk together. At first, when it was suggested that I talk about cats in space, I thought it was a bit ridiculous and that, I wouldn't have, much to say. But then when I started researching it, it actually became quite interesting, and I learned a number of things. And I will warn you that at points this will get a little ridiculous, but I had to find ways to get the ridiculous or get the cuteness of cats in with here is a cat. There you go. In with science. So let's get started. Let me see. Let me get rid of this thing. The first thing that I wanted to introduce you guys to is the term bioastronautics, which is the study of things living in space. Now, this is a critical field for any group that plans to go into kind of microgravity environment or beyond. Because if you think about it, everything that lives on land has evolved there because it's compatible, and everything that lives in water is also, used to those conditions as well. So if you put something in zero gravity, it's confusing and sometimes disruptive. And so to experiment with this, space environment, what we do is we do experiments on a parabolic flight pattern. So this is basically an airplane that travels, as you can see in this graph, right? It goes at kind of like a base level. It starts going up, it inclines till it gets to this peak here and back down. So this pattern right here, where you experience the incline, you're actually experiencing more gravity, more weight on you. It's much like if you go into an elevator and press the up button, right? You feel heavy for a second. That's how it feels on this airplane, but it's a lot more exaggerated because you're moving a lot quicker. And here at the top, this is where you feel a 0G environment. So you don't feel the effects of gravity. And when you start to dive, this is where you start feeling heavy again. So just like if you go in an elevator, you press the down and you start, you press up and then you press down. You know what I'm saying? You get heavy there for a second when the elevator stops. And so this parabolic flight pattern, it normally lasts for, a couple of hours, and they do numerous of these parabolic loops where you get about, 20, 30 seconds of zero gravity simulations. And here is the cockpit of the Mercury astronauts on what is known as the Vomit Comet. As you can imagine, that a flight like this could induce some pretty wicked digestive malfunctions. Anyway, so with the bioastronautics, we have feline bioastronautics. So imagine, or any cat, right? We know just the term, cats always land on their feet, right? They just instinctively know where the ground is and which way is up. And they don't really surrender to any sort of disorientation. So the Air Force put cats on the Vomit Comet in 1947 to study how they reacted to a zero gravity environment. And I have a video that I want to play you. It's fairly short, but it shows you both the before and during the zero-G environment. So here we go.
In these experiments, you can see the disorientation resulting when an animal is suddenly placed in a weightless state. Cats, when dropped under normal conditions, will invariably rotate their bodies longitudinally in midair and land on their feet. This automatic reflex action is almost completely lost under weightlessness. Pigeons normally keep their bodies in a horizontal axis while in flight. These zero-G birds have lost their feeling for what is up or down and point in all directions, some even flying upside down.
I kept the pigeon part in there because I thought that was wicked cool also. So, I mean, this wasn't just animal cruelty, you know, see what happens when you drop a cat, but it actually helped inform scientists how to train our astronauts to maneuver in space, because your instinctual motions when you're in a zero-G environment don't work in space. And so we needed to train our astronauts to do certain things differently. I don't want to see that again. Okay, so back to cats in space, more cats in space. Let's see, this chart over here shows landmarks for animals in space. So in 1947, the first animal was launched in space. I'm going to have you think about that for a second and what you think that the first animal in space was, because I was totally surprised what it was, but I'll get back to that. So cats in space, or Le Chat in space, the French were the first to put cats in space. What they did is they had about 24 cats that were trained for this space travel, this trip to space. The training lasted for about 2 months. They had electrodes implanted like behind their ears, the brain, their back, like kind of all over their body, so they could record responses, and they could also kind of give them like little shocks to see, you know, what would happen. They also, this training also had them put in these kind of 3-axis centrifugal things. So they were kind of like spinned around and see, you know, how, you know, disoriented and stuff they got with simulated rocket noise. Another thing that they did in these training exercises is that they combined these cats in like really tightly wrapped cloth that would kind of simulate, you know, what it would be like for them to have a seat belt on in the aircraft or something like that. And so this is something that's, you know, training that's very similar to humans, but they, you know, also did it with cats, and they picked the most well-temperamented cat to go up into space out of those 14 cats. And this cat was number C341. It was later known as Felicette, the female name of Felix, Felix the cat, because it looks like Felix the cat. You can see it up there in its little space flight suit apparatus thingy. And this was the first cat in space, flew a 13-minute suborbital flight and was safely recovered, which is a good thing because launching animals into space never really had a good track record after the first couple of launches. Anyway, there was a second cat that they tried to launch, but this one exploded at launch, unfortunately. The rest of the cats, they don't really know what happened to the rest of the cats. Felicette was put down a couple months later, and they studied her brain to see, like, you know, effects on her space flight with, you know, her biology. This is actually the first cat memorial statue that was ever made. So this was a Kickstarter that was funded and built by this guy over here, shown in the corner of the cat that's sitting on the world and gazing up the stars. Thought it was kind of neat. Let's see. Feline named for spacecraft. There is something called Super Tiger. which is it stands for Super Transionic Galactic Element Recorder. Folks at NASA are not really great at acronyms, but this is a giant balloon experiment that launches from Antarctica, as you can see over here on the left-hand side of the panel. It's quite big. It goes up into the upper atmosphere, and it looks for heavy cosmic ray events. Another spacecraft that's not yet built yet, it's a concept mission. It's called Lynx. And a lynx is a feline known to have keen eyesight. And in many cultures and traditions, it's a symbol of great insight and supernatural ability to see the true things of nature. And so historically also, Galileo was a proud member of Italy's Accademia dei Lincei. I'm probably butchering the pronunciation of that, but it's Academy of the Lynx. And it was a society devoted to investigate the natural world. I just thought that was quite interesting. It's not just, the name of the telescope. Let's see, more stuff named in space after cats. So this was totally new to me when I was doing this. So Saturn, we all familiar with Saturn and its set of rings, and Saturn also has dozens and dozens of moons. But Saturn also has these things called kittens that orbit its F ring. So these rings, if going out, this very far outermost ring right here, that's the F ring. There's like 60 of them plus. And they're just like baby moons. So they're not big enough to even be small moons, as we call them in astronomy, classify them. And they have names they have cat names like Fluffy and Garfield and things like that. So that's kind of cool. Other things that are named after cats. We have an asteroid that's named after the person who discovered it, Cat, who had a cat who looked like Mr. Spock. And that's what, this is their cat. That's what the asteroid is named after. So that's pretty fun. There is also the Cat's Paw Nebula. You see up here on the far right. It looks like Cat's Paw. This is an emission nebula. So this is basically a stellar nurse born. And then the Cat's Eye Nebula, you can see down here in the bottom. Well, it's behind my head. I just confirmed. It is a gorgeous planetary nebula. So this is all the material and stuff that it is being ejected off of a star after it dies, and you can see the white dwarf that's just left over in the core of it right there. Other feline asteroid name. So this was a really cool story that I learned about also doing my research. Felis was a constellation named by Lalande in 1799. And it was a very well known and documented in all the catalogs books, constellations for back then. And then in 1922, the International Astronomical Union reviewed the names for these things, and it said, no, we don't like that Felis the cat. We don't like that constellation. It's out of here. And they kept 88 constellations. And these are names of the other constellations that they also gave the boot to. They didn't like Manus the penguin, or Limax the slug, or Hippocampus the seahorse. I thought that was quite cute. Anyway, as a resistance movement, Felis is now Calarego. Probably saying that wrong as well, but this is kind of a super constellation that is made up of 7 different constellations. And three of those 7 constellations that it makes up are cats. So we have Leo Major, Leo Minor, and the Lynx. So the next thing I want to convince you guys about is kind of fun, I think. So this is a fundamental relationship between cats and black holes. We saw a picture of Dan Sheehy's cat, Bernie, who is ginormous. And the whole, cat black hole joke has probably been made a whole lot at Bernie's expense. So this image shows a transformation of a cat into a black hole. And I kind of want to look at this a little bit deeper and see if we can, look at it like an astronomer would look at it. So observational evidence of black holes. So this over here on the left is a supermassive elliptical galaxy called Messier 87. This elliptical galaxy is not flat like a frisbee like our own. It's kind of like a big fuzzball, and it has, you know, 1,000,000 times more stars than our own Milky Way has. It's ginormous. And if you see kind of at the 3 o'clock position, there's this blue streak coming out. This is a super luminous jet of material that's flying out from the very center of it. And like many galaxies that we know of, this galaxy has what we call a supermassive black hole in the center. And our galaxy has one of those too, but ours isn't active. This one is active. We call it an active galactic nuclei. And the business that's going on down in the very center around the black hole is producing all this business that is spewing out well beyond the far reaches of the galaxy itself. So astronomers came up with this idea to image the black hole in the center of this galaxy by constructing this Event Horizon Telescope. And the reason why they did this is that since this black hole, even though it's really, really big, it's really, really, really far away. And so to get resolution in astronomy, you need a really, really big telescope. And that can be simulated by stringing telescopes together, as you're seeing here in the globe right here, to kind of synthesize the resolution you get from a giant telescope. Just want to emphasize that these are radio telescope observations, not optical. The importance of that is, actually, that's not very important at all. Anyway, so let me show you what they found. So this is over here on the left. This is the M87 galaxy, that big fuzzball right there. And these are insert right here. This is zooming in where you can see that kind of super luminous jet, the one over here at like the 3 o'clock position. And then you can kind of see a stunted one over there that's kind of showing the foreshadowing of it coming out the backside. And then you see it zoomed in again here. And this right here, this is the first ever image of a black hole that was made by the Event Horizon Telescope. This was made a couple years ago now. This black hole itself is about 65 billion times the mass of our sun. And this it's from the XKCD, but it has, you know, drawn on it the scale of our solar system. So within this black circle right here, we have the black hole. You see Pluto's orbit right around the sun, and then you see where the Voyager spacecraft that we launched out in the 1970s, where that has reached out pretty much to the event horizon of this black hole. So this thing is enormous. So getting back to, you know, where we started out with here, you know, cats and black holes and where their relation. So I wanted to kind of do a little more refined zoom here. So this is the image of a black hole. We'll say this is at 400%, but what if we zoomed out a little bit, and here it is at 300%. Here you have it, 200, and there you go. So, supporting evidence that there is a fundamental relationship between cats and black holes. There you have it. So the next thing that I want to introduce you to is, you know, how gravity works. You have two different ways of looking at gravity. You have Newtonian gravity and have Einsteinian gravity, or general relativity. So both of these are right. They're just kind of, they have different approaches of looking at it. Anyway, that the importance of that is not relevant. So up here in this cartoon, you show the Newtonian gravity. So here we have an orbit of the Earth around the sun. And this, you know, Newton says, okay, forces cause these objects to accelerate, and space and time don't have anything to do with it. Einstein says, well, they actually move from distortions in space, and so space and time depends on a frame of reference. And so here you can see this grid right here where the sun lies, there's actually a little divot. And indeed, if we look at the orbits of Mercury around the sun, it doesn't actually follow a Newtonian gravity prediction, it kind of processes like this, and that's due to general relativity. So it's a bit more accurate when describing motions. And so the reason why I'm pointing this out is that, you have, a massive object, and it kind of depresses this fabric right here, what we're calling space-time. It's distorting space. And the more massive your object is, the bigger distortion of space is going to have, the larger its gravity is going to be. And if you keep on making an object more and more and more massive, right, and into a black hole, you're actually decreasing its size in the end. And here you have a warp of space-time that is warping the fabric way, way, way more than anything smaller than it. So a black hole progenitor is much, much, much larger than the sun, right? Astrophysically speaking, but its condensed size is so much smaller. So if you took our sun and you smushed it into a black hole, it would be about the size of Manhattan. And if you took the Earth and smushed it to the size of the black hole, it would be the size of like a large marble-ish. So observational evidence to support this point. Here you go, a black hole warping space-time, as you can see from the blanket right there. All right, so that might be a little bit of a stretch, but I kind of want to take you into a little bit of a cautionary tale. So it's quite rare for cats to turn into black holes, but I want to prepare you in case something like that may happen. You can see the cat right here. It has that, cat like, I'm looking at you and don't piss me off kind of look with the ears and everything like that. Okay, so where are we on time? Okay, what if your cat turned into a black hole? So as a physicist kind of, sets up a problem, you kind of write down all the facts. And we're going to put this in the perspective of a flea that is leaping from the cat itself, right? So you have, there we go. You have a cat with a mass of 1 kilogram, and it has, an average radius of 0.1 meter. And for this experiment, we're going to treat as negligible the mass of the Earth, air resistance, and the laws of probability, which will definitely be apparent later. So some equations first, right? On the surface of your cat, the flea will have a weight that's given by Newton's law, and then the flea will also have a gravitational potential energy and kinetic energy. You don't need to know anything about these equations, but I just want to let you know that it's backed up by physics. And if I put equations in here, you're more likely to believe me. All right, so big G is the gravitational constant. Big M is the mass of the cat. Little m is the mass of the flea. Big R is distance from the cat. And little v right here is the velocity, so how fast it's moving. Okay, so fast forward ahead. Because of conservation of energy, energy is always conserved. You can set potential energy equal to the kinetic energy and solve for the velocity. And so, as I put here in the first bullet, do some math, and you come up with your escape velocity. So I want you to notice here that the mass of the flea is not involved in this equation. We don't care about flea's mass, right? The escape velocity from the cat is the same for fleas, for porcupines, watermelons, whatever you want. Okay, so for those of you not accustomed to evaluating equations and knowing what they mean, you can think about it this way. Flea hops up, right? And then it comes down. There comes a certain point where it hops up enough where it never comes back down. And that speed where it's hopping off enough where it never comes back down, that is called the escape velocity. Escape velocity of the cat. So have an idea in your head what this number is. I'm going to tell you on the next slide. There you go. The escape velocity of a cat is 0.000037 meters per second. And there is nothing in this world outside government bureaucracy capable of achieving such such a velocity. That's wicked slow. So what if we set the velocity to the maximum? So the speed of light, nothing can go faster than the speed of light. And then we saw that previous equation, not for the velocity, but we want to solve it for what cannot escape, or what size of an object will a cat have to be for light not to even escape. And this is the equation that you're looking at right here. And note that this doesn't just work for feline black holes. This works for the whole deal. So the number that we're looking for, the magic number, is 1.5 times 10 to the minus 27. If you're not used to looking at scientific notation, that's a 0 followed by 20 or 0.26 zeros 1 5. It's super stupidly small. And as we heard in our last talk, we were talking about atoms. Atoms are around 10 to the minus 11 meters. We're talking minus 27, so that's still a good bit smaller than that. Once the cat gets smaller than 10 to the minus 15, right, that's a point and then 14 zeros and then a 1, gravity loses significance because nuclear forces then play a role, and they are 10 to the 40 times stronger than gravity. So whatever, why are we doing this exercise? Anyway, I just wanted to show you that no flea is bound to a cat by feline gravity. So we now know that. Okay. But we started this conversation talking about the flea, and we're going to ignore all the inconvenient facts that, you'll have the nuclear force come in, and this is way too small for a cat ever to be spontaneously made into a black hole. So we'll ignore all those things. So what about the flea? How is the flea feeling right now? So the flea is now trapped to the cat indefinitely, and it weighs 10 to the 52. That's 1 and 52 zeros after it. It weighs more than it was on the pre-black hole cat. That's tough. The next thing that I want you to think about is really cool. So I wanted to compare the effect of feline gravity at different parts of a flea, right? So here in this diagram, we have your very, very, very tiny 1 kilogram cat, right? It's 10 to the minus 27 meters big. It's very, very, very small right here at the tip of that arrow. And our flea hasn't changed, right? It is, still right here. You have a head, and it's all of its feet and its butt. And fleas will say, this flea is 0.001 meters big, right? So here's our extension right here. So we know gravity acts on an object depending on its distance. So if we calculate the force of gravity on the flea's butt, which is basically touching our very tiny 1 kilogram cat, right? And we compare it to the force of gravity on the flea's head, which is 0.001 meters away from that cat, right? We get an enormous change in differential of the gravities that this flea is feeling on its head versus its butt. So the differential is 10 to the 48. So that's 1 and 48 zeros, G's, different from his head to the butt. This is called a tidal force, and this we see often in astronomy, and it has a special word. This is called spaghettification, and I spelled it correctly. I just emphasizing the cat in here. So this is called spaghettification, and this is not good for any flea, obviously. Therefore, natural selection has favored fleas which avoid cats smaller than any hydrogen atoms, and I think we can all agree that that is the case. So on that note, I did want to thank Adam Henrowski, who's a quarantine mathematician, for inspiring this dialogue of what if your cat turned into a black hole. And I can take questions now. Thank you.
All righty. Great talk, Tabby. If you want to unshare your screen. Okay. So as I did with Dan, I'm going to start with some questions about you. First off, it's a very, very basic question. What got you into astronomy? Hi, Pom Pom.
Let's see. I liked all the sciences, and that's kind of what astronomy is, because I mean, it's a bit of physics and nuclear physics and chemistry and biology and geology, and it's everything, right? So I didn't have to pick, and I hate choosing. So that was a win-win.
Alrighty. What does a normal day of work look like for you? I asked Dan, and I'll ask you as well.
Let's see. So I am an astronomer by trade, and I do identify as an observer. So I work with data from telescopes, but rarely do we actually go and look through a telescope. Typically, you either get your data emailed to you, either it's some robot taking it from across the world, so you don't have to take it, or you get data from space. Either is really great. But there is on occasion times where you do get to go to the telescope. You don't look through a telescope, of course. You go and you collect data and you analyze it when you get back. So I don't have a lab, and it's involves a lot of working through data. Lately, I've been dealing with a lot of bad data. That's been not great. But you don't learn anything if you're just given good data. That's what I keep telling myself. And I meet with students, grad students, and undergrad students, and cats. Yeah.
Who inspires you? It doesn't have to be work related, but it can be if you want to go there. But who would you say inspires you?
I don't know. So this is Pom Pom. She's famous. Oh, I forgot my prop. Cat in space. This is Felicia. I actually got this at the NASA headquarters when I visited there. I don't know, it was probably like 5 years ago now. Isn't it adorable?
Very cute.
Yeah. As for who inspires me,
Pom-pom.
Okay. I don't have a good answer for that. I don't know.
That's fine. I just thought I would ask. And then the usual question: what is your favorite Pokemon, Tabby?
Well, I've been instructed to say something. Took a screenshot of it. It is Milotic.
Okay.
Yeah, it's like a crazy serpent thing.
Yes.
Yeah, there you go.
Oh, yes. Is that your Pokemon Go?
That is my Pokemon Go.
Okay.
Yeah. A screenshot of it.
Okay. So to start with the science questions, I will ask the first one. In your research, did you find out why they send different kinds of animals into space? Like, is there something special that cats show that maybe some other animals don't?
Well, okay, so this is, I guess, a quiz for yourself that I'm going to answer now. So the first animals ever in space were fruit flies. You know that? Like, what? Yeah, they put fruit flies on like one of those like high altitude balloons, and they studied radiation coming in on the fruit flies. I did not learn about why they put different kinds of animals into space. I mean, they do like to send primates up there. I think because they're very similar to our own, like they're what, 99 point some, I don't know, very similar to our own DNAs. But, cats and dogs aren't very different, once you get down to the, anyways. And so I don't know why they choose some things over others. I mean, there is an intelligence factor in there too, I think. But,
Okay. Our next question is from the chat. It is from Nikki Fergun, and they ask, can we expect to see any new cats in space in some capacity anytime soon?
What about Pom-pom in space?
Maybe Pom Pom could go to space. What is it that I was? I am not familiar with any program, but I do know that space tourism is like pretty far out and futuristic as it seems, is something that we're going to be seeing a lot more of with all these, private rocket companies, basically billionaires building their own private rocket companies. It's really going to transform the way we see things. And so Bezos's idea of amusement parks in space, I just can't get over how cool that would be. And if you have like a Disney World in space, like why not, bring your cat to, I don't know, or your dog to a dog park in space. It'd be expensive, but hey, with the graphene space elevator, it may be possible.
Yeah. Isn't there something like they're trying to build telescopes on the moon and stuff, like more different kinds of telescopes in space?
Yeah, it's all a work in progress.
Yeah. Okay. And then another question from the chat. Do you know if the French-American cat programs had a catchy name like the U.S. AstroChimp program did?
No, the Chat Suspect. That's what I read. I do know that one of the cats. Wait, was it the cat? Oh darn! I'm getting mixed up on my research here. But one of the animals they sent to space, and I think it was either the French or the Russians. They came back and they had puppies or kittens, whichever it was, and they gave it to JFK's kids as a present.
I thought, wasn't that Laika's puppies?
No, because Laika died.
Oh.
So it might have been like a future one.
Okay.
Getting mixed up in the stories.
I remember you telling me the story. I just don't remember the important part. Okay, and then you talked about the kittens, Saturn's kittens.
Mm-hmm.
You said that they were like too small to be moons.
Mm-hmm.
Now, I don't study moons or exoplanets. How small do you have to be too small to be a moon? Does that make sense?
Yeah, that totally makes sense. So in the outer solar system, all the giant planets, they have like dozens and dozens and dozens of moons, and we can categorize them. We categorize them into small, medium, and large. And basically, from what I knew until I was writing this doc, is that the small, they didn't have any, they weren't big enough for gravity to make them into a circle or anything like that. They and so I just thought that would encompass everything. But these little moonlets, or kittens, apparently don't have enough gravity to influence the environment around them. So a lot of the small moons around the Jovian planets have a job, in a sense. So they're like, I had on that slide, they're shepherd moons. So basically, like they keep the ring in shape, and they kind of like push it around and make sure that it stays in kind of its ring format just by the way it orbits and the way it gravitationally interacts with all the particles inside the ring. And so I think moonlets are larger than a little ringlet particle, right? But it's not large enough to influence, its environment and have a job.
Interesting. Huh. Well, thanks again for your awesome talk. Dan has gone missing from the call, but I want to thank both of you very much for graciously volunteering to talk to all of our viewers today. And we know you're both really busy, but we're thankful for you. Before we head out, shout out again to our streamers, Allie and Alex, and also Cassidy and Pom Pom, who participated in Tabby's talk.
Oh, since Dan is not here, one of my favorite things to do is beat him in Words with Friends. He says he likes crossword puzzles. He's going to regret leaving early now.
Good. If you are watching us asynchronously and not live, feel free to still interact with this video. It would really help us if you subscribe to our channel. That would give you notifications for our next show. And be sure to like this video. Axel has also made an appearance now. So definitely keep an eye on our Facebook, Instagram, and Twitter, where we post about all of our events as soon as we have information. And do please, if you are feeling generous, please consider donating. But we will see you all here again next month, where we'll have 2 more speakers and some more fun stuff to talk to you guys about. Until then, bye-bye, everyone.